48 light-years away, a planet drowns in clouds made of battery acid. Its atmosphere weighs 90 times heavier than ours. The ground glows from heat that melts zinc. Scientists just proved this world is a super Venus. James Webb found chemistry there that forces us to rewrite what planets can become. If this sounds impossible, hit subscribe. You'll want to see where this goes. Breathe deep. We're entering a world that kills everything. Astronomers aimed James Webb at something called GJ1214b. The planet sits in Ophiuchus, close enough that its atmosphere should reveal secrets. What came back from Webb's sensors made 3 separate research teams check their math. Carbon dioxide everywhere. The spectrum showed absorption lines matching Venus almost perfectly. 96% of this world's air is carbon dioxide, the same greenhouse gas cooking Venus into a furnace. This planet weighs more than Earth. It's smaller than Neptune. For years, scientists argued whether worlds this size were rocky super-Earths or icy mini-Neptunes. Webb ended the debate with one observation. GJ1214b is neither. It's something new, a super-Venus. The discovery changed everything. Now, we had a laboratory for Venus conditions without sending probes. Every measurement from this distant hell teaches us about the hell next door. Temperature patterns, cloud chemistry, how greenhouse effects spiral out of control. Finding one super Venus raised a darker question. How many planets out there followed this path? How many worlds started like Earth and ended as poison ovens? The math suggests Venus planets might be common. Any rocky world orbiting too close to its star faces the same fate. Water evaporates. Carbon dioxide builds up. The atmosphere becomes a death trap. The super Venus category might hold millions of dead worlds. Webb showed us GJ1214b probably had oceans once. Chemical signatures hint at water that boiled away billions of years ago. The planet likely started habitable. Something tipped it into runaway heating. Now it's a warning written in starlight. Scientists compared every detail to Venus. The similarities were disturbing. Both likely began with liquid water. Both accumulated crushing carbon dioxide atmospheres. Both reached temperatures that would vaporize lead. Both became planetary graveyards. What Webb revealed 48 light-years away was a mirror. Venus staring back at us from another star system. But Venus itself holds stranger mysteries. 4.5 billion years back, Venus and Earth were nearly identical. Same size within a few hundred miles. Same rocky makeup. Same distance class from the star. Both formed from the same swirling disk of dust and gas. They should have evolved together. Something broke Venus. The planet orbited 45 million miles closer to the heat. That difference sounds small. In planetary terms, it's the line between life and death. Venus absorbed about twice the stellar energy Earth receives. At first, this didn't matter. The young star burned dimmer. Venus might have been comfortable. Then the star brightened. It happens to all stars as they age. More fusion, more energy, more radiation flooding outward. Earth's orbit kept it safe. Venus's orbit put it in the danger zone. Water vapor began trapping heat. More heat meant more ocean evaporation. More water vapor meant more trapped energy. The loop fed itself. Within perhaps a billion years, the feedback became unstoppable. Venus entered what scientists call runaway greenhouse. The oceans boiled. Water vapor rose high where ultraviolet radiation tore molecules apart. Hydrogen atoms, weighing almost nothing, drifted into space. Oxygen reacted with rocks, turning the surface red with rust. The water that might have filled seas vanished molecule by molecule. Carbon dioxide from volcanoes had nowhere to go. On Earth, oceans absorb carbon dioxide. Marine life locks it in shells. Rain washes it into rocks. Venus had no water to capture the gas. Every volcanic eruption added more carbon dioxide. None ever left. The atmosphere thickened until it became a pressure cooker. Temperature differences between day and night disappeared. The thick air moves heat so efficiently that Venus's night side stays nearly as scorching as the day side. Nowhere on the surface offers relief. 470 degrees Celsius everywhere, always, forever. Atmospheric pressure built to 93 times Earth's. Standing on Venus would feel like swimming 900 meters underwater. The weight alone would crush your ribcage before the heat could cook your organs. Sulfuric acid clouds formed from volcanic sulfur and photochemical reactions. These yellow layers wrap the whole planet 65 kilometers deep. They bounce back 3/4 of incoming starlight. Venus shines brighter than anything in Earth's sky except the moon. The planet scientists imagined might have jungles became the solar system's torture chamber. Earth's twin transformed into Earth's nightmare. Then astronomers found something in those acid clouds that chemistry says cannot exist. 2020 brought an announcement that split the scientific world. Researchers detected phosphine in Venus's atmosphere. The molecule is simple: one phosphorus atom holding 3 hydrogen atoms. On Venus, it represents an impossibility. Phosphine should not survive in an oxidizing environment. Venus's atmosphere wants to rip apart any reduced molecule. Carbon exists as carbon dioxide. Sulfur exists as sulfuric acid. Everything gets oxidized to its maximum state. Phosphine, a reduced molecule, should last seconds before breaking down. On Earth, phosphine comes from 2 places. Industrial factories produce it for semiconductors. Bacteria make it in oxygen, poor swamps, and animal guts. Finding it on Venus suggested one of 2 shocking possibilities. Unknown chemistry creates it through processes we've never seen, or life produces it in those acid clouds. The detection came from radio telescopes. The James Clerk Maxwell Telescope in Hawaii picked up a signal. The Atacama Large Millimeter Array in Chile confirmed it. Both saw absorption at exactly the frequency where phosphine swallows radio waves. The signal appeared between 40 and 60 kilometers altitude, right in the cloud layers. Calculations showed about 20 parts per billion of phosphine. That's incredibly tiny. It's also incredibly impossible to explain through known processes. Lightning might generate trace amounts. Volcanoes could inject some. Meteor impacts might contribute. None of these sources came close to producing enough. The controversy exploded. Other scientists reanalyzed the data. Some claimed the signal was actually sulfur dioxide interference. Others questioned the statistical methods. The original team revised their numbers downward, yet insisted phosphine was there. Research groups split into camps. Believers argued for life in the clouds. Skeptics demanded better proof. A third group proposed exotic volcanic chemistry that textbooks don't describe. The debate grew heated. Careers and reputations hung on which interpretation proved correct. James Webb promised to settle the question. Its infrared instruments could measure atmospheric composition with precision previous telescopes never achieved. Webb could detect phosphine if it exists. It could rule it out if the signal was an artifact. The phosphine mystery highlighted something embarrassing. We barely understand our neighboring planet's chemistry. Decades of missions mapped the surface. Probes sampled the atmosphere. Yet the chemical processes in those clouds remain largely unknown. What else might be hiding in that acid haze? The chemistry gets stranger still. The clouds floating between 40 and 70 kilometers altitude represent Venus's least terrible zone. Temperature there ranges from room temperature to hot bathwater. Pressure approaches what you'd feel at sea level on Earth. If you could survive the acid, this layer might almost be tolerable. Almost. The droplets are concentrated sulfuric acid, 75 to 90% pure, strong enough to dissolve flesh in seconds. These drops form when volcanic sulfur dioxide rises and reacts with trace water vapor. Ultraviolet energy from the star drives the chemistry that creates acid from simpler ingredients. Scientists have tracked weird things in these clouds for decades. Particles that are not perfectly round, unlike pure acid droplets, water vapor at levels that shift unexpectedly, oxygen that has no business being there, sulfur dioxide concentrations that change in ways models cannot predict. Each anomaly whispers that something complex is happening. One theory proposes dust swept from the surface could react with acid. Venus has fierce winds in the upper atmosphere. These could lift minerals high enough to reach cloud level. Calcium carbonate or other rocks might neutralize some acid, creating salts and releasing gases. The math shows this would need enormous amounts of dust, more than wind could reasonably carry. Laboratory work revealed a shocker. Simple organic molecules can form in sulfuric acid under Venus conditions. Formaldehyde, created by light-driven chemistry in the gas phase, dissolves in acid drops. Once there, it reacts with carbon monoxide to build two carbon species, like glycolic acid. These molecules show surprising toughness, lasting days at cloud temperatures. This contradicted 50 years of assumptions. Scientists dismissed organic chemistry on Venus because acid should destroy it. New experiments proved very simple, organics could survive and even participate in building more complex molecules. The acid drops became potential factories rather than just destructive blobs. Could life exist in these drops? On Earth, certain bacteria thrive in battery acid. They've evolved enzymes that work in pH below 0. Some microbes live in mine drainage more acidic than Venus's clouds. If Earth bacteria could adapt this far, might Venus life have gone further? The theoretical Venusian microbes would spend their existence suspended in acid. They might eat sulfur compounds, using them for energy the way we use oxygen. They could produce ammonia as waste, which would neutralize acid around them, creating tiny pockets of survivable space. The idea sounds insane. The chemistry checks out. The ammonia hypothesis explains multiple mysteries at once. If life makes ammonia, it dissolves in acid drops, turning liquid spheres into salt-like slurries. This matches the non-round particles. Ammonia would make sulfur dioxide dissolve more readily, explaining concentration variations. Ammonia reactions release oxygen, explaining that anomaly too. Extraordinary claims need extraordinary proof. Before declaring Venus hosts cloud-dwelling microbes, we need direct measurements. We need to find the ammonia. We need to identify specific waste products from metabolism. We need to eliminate every possible non-biological explanation. What scientists do know is the clouds are more chemically active than anyone guessed. Whether that activity is geological, photochemical, or biological remains the question driving the next generation of Venus missions. Meanwhile, the surface below those clouds makes hell look inviting. Step onto Venus, and you would die before feeling pain. The heat would end you faster than poison or pressure. 470 degrees Celsius, 878 degrees Fahrenheit. Hot enough that metals glow red, hot enough to make rocks luminous. This temperature blankets the entire surface. Day, night, equator, poles. Everywhere measures within a few degrees of this killing heat. The greenhouse effect operates at maximum possible efficiency. Stellar light penetrates clouds and warms the ground. The heated surface radiates infrared, trying to cool. The dense carbon dioxide atmosphere absorbs every bit of that infrared. None escapes. All gets trapped, reheating the air, which heats the surface more. Even the night side offers no mercy. Venus rotates so slowly that one day lasts longer than 1 year. Night at any spot continues for months, yet temperature barely drops. The thick atmosphere moves heat sideways so effectively that the dark side stays within degrees of the lit side. The whole planet maintains thermal equilibrium at a level that defies imagination. The ground actually glows from its own heat. If you could stand on Venus at midnight with human eyes, You would see rocks emitting dull orange light. Everything around you would be luminous from thermal radiation. The landscape bathed in eerie, self-generated glow, even without any starlight. Soviet landers sent in the 1970s and 80s survived briefly. The Venera missions managed to send data for up to 2 hours before electronics failed. The longest survivor, Venera 13, transmitted for 127 minutes. Then, the heat cooked its circuits beyond function. The images they sent back showed flat basaltic plains, fractured rock everywhere, orange sky from dense atmosphere scattering light, no water erosion, no wind weathering, just heat-cracked stone under crushing weight. The pictures looked like foundry floors in industrial smelters. Mercury orbits closer to the star, yet never gets this hot. Mercury lacks atmosphere to trap heat. Its night side freezes. Venus's thick carbon dioxide blanket makes it the hottest planetary surface in the solar system, hotter than Mercury's day side, hotter than any natural place in human experience. The heat destroys minerals stable on Earth. Carbonates decompose, sulfates break down. Only the toughest rocks survive. The basaltic composition suggests volcanic activity resurfaced the planet relatively recently in geological time, within the last few 100 million years at most. Some regions show hints of ongoing volcanism. Sudden spikes in sulfur dioxide hint at fresh eruptions pumping gas into the air. Confirming active volcanoes requires observations better than past missions managed. The environment destroys instruments too quickly for long-term surface monitoring. Temperature creates a barrier past technology barely crossed. Future Venus landers need materials that resist heat beyond industrial furnaces. Electronics that function when circuit boards would melt. Cooling systems that work without water or evaporation. The heat makes Venus more hostile than deep ocean floors or polar ice or radiation-soaked moons. Pure thermal energy attacks everything. No material escapes its effect. Yet Venus once had water covering its surface in liquid form. Venus held oceans billions of years ago. The proof sits in atmospheric chemistry. The ratio between deuterium and regular hydrogen tells a story of catastrophic loss etched in isotopes. Deuterium is heavy hydrogen with an extra neutron. When water escapes atmosphere, light hydrogen flies away easier than heavy deuterium. Over geological time, the remaining air becomes enriched in deuterium. The ratio climbs higher and higher as more hydrogen vanishes into space. Venus shows deuterium to hydrogen ratios 100 to 150 times Earth's values. This massive enrichment screams that Venus lost enormous hydrogen quantities. Since rocky planets get hydrogen mainly from water, lost hydrogen means lost oceans. The process took billions of years. Ultraviolet radiation from the star split water molecules high in atmosphere. The reaction breaks water into hydrogen and oxygen. Hydrogen, incredibly light, achieved escape velocity and drifted away. Oxygen reacted with surface rocks, oxidizing iron and other metals into rust. Calculations based on isotope ratios suggest Venus started with water amounts similar to Earth's. Some models propose even more. If true, young Venus could have had oceans kilometers deep covering most surface area. The early planet might have been blue with water vapor clouds instead of acid. The runaway greenhouse doomed that water. Rising temperatures increased evaporation. More water vapor meant more greenhouse heating. More heating meant more evaporation. The feedback accelerated until oceans boiled completely dry. No water remained in liquid form anywhere. Water vapor rose into upper atmosphere, where stellar radiation tore molecules apart. Freed hydrogen atoms moved fast enough to escape Venus gravity. They streamed away in a process continuing perhaps 1 billion years or more. Gradually, all the hydrogen that once filled seas drifted into interplanetary space. Today, Water on Venus exists only in traces. The atmosphere holds about 30 parts per million water vapor. Earth's atmosphere, depending on location and weather, typically contains much higher concentrations. What little water Venus retained gets bound in sulfuric acid molecules or locked in surface rocks. The missing water represents one of planetary science's great transformations. A world potentially hosting rivers, lakes, and seas became a desiccated wasteland. The process warns about greenhouse feedback loops and climate tipping points. Once certain thresholds get crossed, recovery becomes impossible. Could Earth suffer identical fate? Eventually, yes, though not soon. Earth orbits farther from stellar heat, receiving less radiation. Our planet has perhaps 1 billion years before facing similar thermal stress. The lesson of Venus's lost oceans remains sobering regardless. Atmospheres can change radically. Water can be lost permanently. Planets can cross points of no return. Venus demonstrates what happens when a world loses its water and chemistry prevents getting it back. The hydrogen escaped. The oxygen rusted rocks. The deuterium stayed behind as evidence. Every measurement of that deuterium ratio is a gravestone for an ocean. The weight of what replaced those oceans would crush you flat. Stand on Venus's surface, and 93 times Earth's sea level pressure bears down. That equals being submerged 900 meters underwater, deeper than most submarines can safely dive. Deep enough to compress your body like a trash compactor crushing a can. Human bones would crack, organs would rupture, even submarine hulls would strain under such force. Spacecraft landing on Venus need construction like deep-sea vessels with thick pressure shells and minimal weak points where atmosphere could crush inward. The pressure comes from sheer atmospheric mass overhead. Venus's air extends much higher than Earth's and contains far more gas molecules. Carbon dioxide is denser than Earth's nitrogen-oxygen mix. All that mass pressing downward creates immense force at ground level. This pressure affects everything about how the environment operates. Gases behave differently at such high compression. Chemical reactions that would be slow or impossible at Earth conditions proceed readily under Venus's crushing atmosphere. The carbon dioxide itself approaches supercritical state in some regions, existing between gas and liquid phases. Soviet Venera landers provided the only direct surface pressure measurements. These spacecraft, built like armored tanks, descended through atmosphere and survived just long enough to transmit data before heat and pressure destroyed them. Their measurements confirmed model predictions. Surface pressure on Venus exceeds anything naturally occurring on Earth outside deep ocean trenches. Walking on Venus, if you could somehow survive, would feel bizarre. Dense atmosphere would slow movements, creating drag like moving through water. Sounds would travel differently. Light would scatter and refract through thick air in unusual ways. The horizon would appear closer due to atmospheric haze density. Wind near ground level moves slowly because of high pressure resistance. Higher in atmosphere, fierce winds race around the planet at speeds exceeding 350 kilometers per hour. These super-rotation winds move faster than the planet rotates itself, completing circuits around Venus in just 4 Earth days, despite the planet's glacial rotation. The pressure gradient from surface to cloud tops drives complex circulation patterns. Hot air rises from ground level, expands climbing into lower pressure regions, cools, and sinks back at the poles. This circulation redistributes heat and creates planet-wide temperature uniformity. Future missions to Venus must account for this crushing force in every design choice. Landing gear must support spacecraft weight plus atmospheric pressure, trying to compress it. Seals must prevent atmosphere from crushing into gaps. Materials must resist deformation under sustained pressure loading. Electronics must function in environments where pressure alone would damage conventional circuit boards. The pressure makes Venus's surface among the most extreme environments in the solar system. Colder places exist on outer planet moons. More radiation-bathed places exist near Jupiter. For pure physical crushing force applied uniformly and relentlessly, Venus stands alone among terrestrial worlds. No spacecraft has survived there longer than a few hours. The longest record is 127 minutes. The pressure contributes to that short survival time, working alongside heat to methodically destroy every mechanical and electronic system. Understanding this pressure environment means understanding how gas giant atmospheres work, how supercritical fluids behave, how materials fail under sustained compression. Venus is a laboratory for extreme pressure physics, but pressure alone did not create the phosphine mystery. Explosive volcanism might solve the phosphine puzzle. Deep in Venus's interior, where pressure and temperature reach extreme values, phosphorus could exist as phosphide. If volcanic eruptions bring this material to surface and inject it high into atmosphere, reactions with sulfuric acid could efficiently produce phosphine. The chemistry works in laboratory tests. Mix phosphide with sulfuric acid and phosphine forms readily. The reaction needs no complex biology or unknown atmospheric phenomena. Simple volcanic delivery of reduced phosphorus compounds could explain phosphine observations without requiring life. This explanation demands active volcanism, specifically the explosive kind powerful enough to inject material high into atmosphere. Gentle lava flows would not work. The eruptions need to punch through surface and hurl chemicals into cloud layers where phosphine gets detected. Evidence for recent volcanism has accumulated over decades. The Magellan radar mission in 1990s mapped volcanic features across the surface. Vast lava plains cover much of the planet. Shield volcanoes rise kilometers above surrounding terrain. Calderas mark collapsed summits of volcanic mountains. Some features look geologically young. Fresh-appearing lava flows show minimal weathering signs. Certain regions display characteristics suggesting eruption within the last few million years. Confirming current volcanic activity requires catching eruption in progress or detecting its immediate chemical signature. Sudden sulfur dioxide spikes provide tantalizing hints. Several spacecraft detected temporary increases in atmospheric sulfur dioxide that fade over months or years. These spikes match patterns expected from fresh volcanic eruptions, releasing gas into atmosphere. As sulfur dioxide reacts with other atmospheric components and forms sulfuric acid, the spike dissipates. The phosphine detection, if real, could represent another volcanic signature. If eruptions inject phosphide into atmosphere, resulting phosphine would be destroyed by photochemistry and acid reactions over time. Maintaining observable levels requires ongoing volcanic activity, continuously replenishing phosphine as fast as destruction removes it. This hypothesis makes testable predictions. If volcanism produces phosphine, the gas should correlate with other volcanic markers. Regions with elevated phosphine should also show increased sulfur dioxide. Temperature anomalies from recent lava flows should appear near phosphine concentrations. Multiple chemical signatures should align geographically and temporally. James Webb's discovery of super-Venus planets provided unexpected support for volcanic explanation. Brown dwarf studies that Webb conducted found phosphine in atmospheres where only geological processes could possibly operate. This demonstrated phosphine can arise without biology under appropriate conditions. The finding proved assuming biological sources was premature. Geological phosphine production was possible even if specific mechanisms remained unclear. The brown dwarf detections shifted the debate from life versus chemistry to which chemistry pathway operates. Understanding Venus's volcanism requires better observation tools, spacecraft surviving surface environment long enough to monitor seismic activity, orbiters with instruments sensitive enough to detect thermal signatures of fresh eruptions, atmospheric probes sampling gases directly and measuring isotopic compositions. The volcanic hypothesis for phosphine represents intersection of geochemistry, atmospheric science, and planetary geology. It shows how different planetary processes can connect in unexpected ways. Whether volcanism explains phosphine or something stranger is happening, the chemistry unfolding in Venus's clouds defies simple explanation. James Webb aimed its infrared sensors toward Wolf 1130c, a failed star drifting in cosmic darkness. This brown dwarf, too small to sustain hydrogen fusion, holds temperatures and pressures creating unusual chemistry. What Webb found changed the Venus conversation completely. Phosphine, clear spectral signatures at concentrations around 0.1 parts per million. The same molecule sparking controversy on Venus. This time, life was impossible. Brown dwarfs have no surface, no temperate zones, no chemical ingredients necessary for biology as we understand it. The detection proved geological processes alone can produce phosphine in planetary mass objects. Theoretical models had predicted this. Gas would form deep in hot interior where temperatures and pressures enable reduction chemistry. Convection currents would transport phosphine upward faster than photochemistry could destroy it. The same mechanisms work in Jupiter and Saturn. Both giant planets show phosphine in their atmospheres. The molecule forms in deep interiors and rises through convection. Phosphine presence on gas giants never sparked controversy because nobody suggested biological sources. Wolf 1130c matched predicted phosphine abundance precisely. Its detection validated atmospheric models. More importantly, it demonstrated phosphine could arise from chemistry alone without any biological contribution. The brown dwarf became laboratory for understanding how reduced molecules persist in oxidizing atmospheres. Here is what puzzled researchers. Many brown dwarfs that should have detectable phosphine show none. Models predict these objects should produce the gas. Their temperature and pressure profiles match brown dwarfs displaying phosphine, yet instruments cannot find it. Something about brown dwarf atmospheric chemistry remains incompletely understood. This mystery parallels the Venus situation. If phosphine should exist based on models yet gets undetected, does that mean models are wrong? Or detection methods lack sensitivity? Could destruction mechanisms exist that models omit? The brown dwarf discovery complicated Venus interpretation. It showed phosphine can exist without biology. It also revealed predicting when and where phosphine appears remains challenging even for objects where life is impossible. Researchers studying Venus like exoplanets took note. The super-Venus planet Webb, characterized, likely operates under similar principles. If that planet shows phosphine, would it indicate volcanism? Unknown atmospheric chemistry? Something else entirely? The connection between brown dwarfs, gas giants, and rocky planets highlights how planetary science benefits from studying diverse objects. Chemistry seeming exotic on Venus might be common elsewhere under different conditions. Molecules indicating biology in one context might arise abiotically in another. Understanding phosphine requires understanding the full range of environments where it can form and persist. Brown dwarfs provide one puzzle piece. Jupiter and Saturn provide another. Venus, if it truly has phosphine, provides a third piece representing rocky planet volcanism. Webb's contribution shows how modern instruments enable comparisons across vastly different object types. The same telescope, peering billions of light years into early universe, can also study brown dwarfs and characterize exoplanet atmospheres. Each observation feeds broader understanding of how chemistry works throughout cosmos. The phosphine debate shifted from, does this mean life, to what does this tell us about planetary processes? That shift represented scientific progress, even if it disappointed those hoping for alien biology signs. The chemistry happening inside Venus's acid drops gets stranger still. Inside each microscopic sulfuric acid droplet floating in Venus's clouds, chemistry happens that would shock terrestrial chemists. For 50 years, scientists assumed concentrated acid would destroy organic molecules instantly. Recent experiments demolished that assumption. Researchers created Venus conditions in laboratory vessels: concentrated sulfuric acid, carbon dioxide atmosphere, temperatures matching cloud layer. They introduced simple molecules and watched. Results surprised everyone. Formaldehyde, a one-carbon organic molecule produced by light-driven chemistry in Venus's gas phase, dissolves in sulfuric acid droplets. Once dissolved, it does not decompose immediately. Instead, it reacts with carbon monoxide, also dissolved from atmosphere, to form glycolic acid. This two-carbon organic molecule shows remarkable stability in concentrated acid. The glycolic acid persisted for days at cloud layer temperatures. Higher temperatures accelerated decomposition, yet even then, the molecule survived long enough to participate in further reactions. This opened possibilities for building more complex organic species through sequential chemical steps. The key insight recognized that thermodynamics and kinetics operate differently. Thermodynamically, most organics are unstable in concentrated sulfuric acid. They should not exist at equilibrium. Kinetically, however, reactions destroying them can be slow. During that window of kinetic stability, other reactions can occur. Carbon monoxide dissolved in sulfuric acid exists in an unusual protonated form. This activated species reacts more readily than neutral carbon monoxide would. The acid essentially catalyzes reactions that would not proceed in neutral water. The highly acidic environment, rather than being purely destructive, enables specific synthetic pathways. Computational chemistry helped map these reaction mechanisms. Researchers calculated activation energies for different steps. They identified which molecules would form first, how quickly they would react further, and what products would result. The picture emerging showed droplet chemistry far richer than previous models assumed. This chemistry matters for understanding cloud properties. If organic molecules form in droplets, they could affect how light scatters through clouds. They might influence droplet size distribution. They could potentially serve as condensation nuclei for new droplet formation. The cloud layer might host complex chemical ecosystem driven by light-driven reactions and acid catalysis. The findings also revived habitability questions. If simple organics survive and react in Venus's acid droplets, could more complex molecules form? Could metabolic pathways operate under such conditions? Experiments proved the chemical barrier was lower than thought. Microbial life on Earth adapted to extremely acidic environments. Bacteria thrive in mine drainage with acidity beyond battery acid. These extremophiles developed enzymes functioning in conditions that would denature most proteins. If evolution produced such adaptations on Earth, perhaps it could on Venus as well. The droplet chemistry research highlighted how much laboratory work remains necessary. Scientists need to test more complex molecules. They need to explore longer reaction times. They need to investigate how ultraviolet radiation affects chemistry. Each experiment reveals new possibilities and raises new questions. Understanding what happens inside Venus's cloud droplets requires bridging multiple disciplines: organic chemistry, atmospheric science, light-driven chemistry, thermodynamics, planetary geology. The interdisciplinary nature makes it challenging yet scientifically rich. What seemed like closed question reopened into active investigation. The acid droplets, rather than being simple sulfuric acid spheres, emerged as potential sites for complex chemical processes shaping the planet's atmosphere in unexpected ways. But what if those droplets contain something actively fighting back against the acid? Scientists proposed a radical idea. What if life on Venus produces ammonia to neutralize acid around itself? This hypothesis could explain multiple cloud anomalies, puzzling researchers for decades. It requires accepting biology might operate in one of the solar system's most hostile environments. Ammonia is one nitrogen bonded to 3 hydrogen atoms. It is a base, the chemical opposite of acid. When ammonia dissolves in sulfuric acid, it neutralizes through simple reaction. The result is ammonium sulfate, a salt, plus water. The formerly lethal acid becomes much less hostile. If microbes in Venus's clouds produced ammonia as metabolic waste, they would create tiny neutral pockets around themselves. These pockets would be less acidic than surrounding droplets. Potentially habitable microenvironments where further biological chemistry could proceed without immediate destruction. The ammonia hypothesis makes specific testable predictions. Neutralizing sulfuric acid with ammonia would transform liquid droplets into solid or semi-solid particles. This would explain observed non-spherical particles in Venus's clouds. Pure sulfuric acid forms perfect spheres from surface tension. Ammonium sulfate crystals are irregular. Ammonia in droplets would also cause more sulfur dioxide to dissolve from atmosphere. Sulfur dioxide shows unusual concentration variations in Venus's clouds. The ammonia hypothesis provides explanation through biology, affecting local sulfur dioxide levels via acid neutralization chemistry. Production of ammonia through the most efficient biological pathway would also release oxygen. This could account for mysterious oxygen traces detected in clouds. No known light-driven or volcanic process explains that oxygen well. Biology producing ammonia would generate it as byproduct. The challenge with ammonia hypothesis is detecting ammonia itself. No spacecraft directly measured ammonia in Venus's atmosphere. Past missions were not looking for it specifically and might not have had instruments sensitive enough to detect it if present. The hypothesis predicts ammonia concentrations that could easily fall below detection limits of older instruments. Lightning strikes and volcanic eruptions can both produce ammonia through geological routes. Researchers calculated whether these sources could generate enough ammonia to explain cloud anomalies. The answer was no. Lightning and volcanoes would fall short by orders of magnitude. Only continuous biological production seemed capable of maintaining required ammonia levels. This does not prove life exists on Venus. It proves that if the ammonia hypothesis is correct, geological explanations are insufficient. The hypothesis itself might be wrong. Other chemical processes not yet identified might explain anomalies without requiring ammonia at all. Future missions to Venus need instruments specifically designed to detect ammonia. They need to measure its concentration at different altitudes and locations. They need to determine whether it varies with time or remains constant. They need to search for other metabolic byproducts that would accompany biological ammonia production. The ammonia hypothesis represents creative scientific thinking, advancing understanding even when wrong. By making specific predictions, it creates testing opportunities. By explaining multiple independent observations with single mechanism, it offers explanatory power. Right or wrong, it drives research forward. If life did evolve to produce ammonia on Venus, it would be fundamentally different from Earth's surface biology. Organisms spending entire existence suspended in air, metabolizing sulfur compounds instead of carbon-based organics, neutralizing acid as survival strategy rather than hiding from it. Such life would rank among the most profound discoveries in human history. Proving it exists requires evidence stronger than unexplained chemical anomalies. The tools to find that evidence are being built right now. James Webb operates at wavelengths invisible to human eyes. Infrared light reveals heat signatures and molecular vibrations that visible light cannot detect. This capability makes Webb perfect for studying atmospheres, even ones it cannot observe directly due to orbital position. The super-Venus discovery hinged on infrared spectroscopy. When light passes through planet atmosphere, molecules absorb specific wavelengths. Each molecule has unique absorption pattern, like fingerprint. By measuring which wavelengths are missing from light, scientists identify which molecules are present. Carbon dioxide absorbs strongly in infrared. The molecule's vibrations resonate at specific frequencies, pulling energy from passing infrared radiation. Webb's spectrograph breaks incoming light into component wavelengths with extreme precision, revealing these absorption features clearly. Measurements from GJ1214b showed carbon dioxide absorption lines at exactly wavelengths expected for Venus-like atmosphere. Absorption strength indicated high concentrations. The pattern ruled out other possible atmospheric compositions. Data pointed unambiguously to carbon dioxide-dominated world. Infrared observations can penetrate clouds blocking visible light. Venus's thick sulfuric acid haze prevents optical telescopes from seeing surface. Certain infrared wavelengths pass through clouds more easily. Some heat from surface escapes as infrared radiation carrying information about temperature and composition. Webb's infrared sensitivity also enables detection of trace gases. Molecules present at just a few parts per million can leave detectable signatures if Webb integrates light over long enough periods. This makes searching for biosignatures or volcanic markers possible even when compounds exist at very low concentrations. The telescope's large mirror collects more light than smaller instruments, improving sensitivity further. More photons means better signal-to-noise ratio. Better signal-to-noise means distinguishing real spectral features from noise and artifacts. This capability proved essential for super-Venus confirmation. Temperature measurements come from infrared observations. Hotter objects emit more infrared radiation at shorter wavelengths. By measuring infrared spectrum, scientists determine atmospheric temperature at different altitudes. This reveals temperature structure, driving circulation, and weather. Webb cannot point at Venus directly because of design. The telescope sits at a point in space where its heat shield must always face toward Earth and the star to keep instruments cold. Venus orbits closer to the star than Earth, so observing it would require Webb to turn toward heat source, potentially damaging sensitive infrared detectors. Webb can observe Venus-like exoplanets around other stars. It can study brown dwarfs with phosphine in atmospheres. It can characterize worlds in Venus, zone of distant solar systems. Each observation builds understanding applicable to Venus itself. The super-Venus discovery demonstrated this indirect approach. By finding planet around another star with Venus-like chemistry, Webb provided laboratory for testing hypotheses about atmospheric processes. The distant world becomes proxy for understanding our neighboring planet. Future Venus-focused missions will use similar infrared techniques from different platforms. Orbiters around Venus itself can use infrared instruments to map heat emission from volcanoes. Atmospheric probes can measure infrared absorption to analyze gas composition during descent. Lessons learned from Webb's exoplanet observations inform design of these Venus-specific missions. Infrared astronomy transformed planetary science by revealing chemistry and temperature invisible to other methods. Webb represents cutting edge of this technology, pushing sensitivity and resolution to new levels. Its discoveries about Venus-like worlds millions of light years away circle back to deepen understanding of the planet just next door. But understanding Venus means understanding the zone where planets go to die. Astronomers coined Venus zone to describe regions around stars where planets become too hot for liquid water yet retain atmospheres. It is a danger zone where worlds transform from potentially habitable to scorched wastelands. The boundary between possibility and death. The concept emerged from studying Venus itself. The planet orbits at distance where early in solar system history it might have maintained liquid water. As the star brightened over billions of years, Venus crossed threshold. Greenhouse effect ran away, oceans boiled off. The world became inferno we observe today. Other stars have Venus zones scaled to their brightness and temperature. Cool red dwarf stars have Venus zones very close in. where planets would orbit every few days. Hot, bright stars push Venus zone farther out, potentially affecting planets in orbits comfortable around our star. Finding planets in Venus zone matters for understanding planetary evolution. These worlds represent transition between habitable and uninhabitable. They show what happens when greenhouse forcing exceeds a planet's ability to regulate temperature through geological processes. The super-Venus planet GJ 1214b orbits squarely in its star's Venus zone. Discovery confirmed Venus-like atmospheres do form in this region. The planet receives more stellar radiation than Earth, yet less than Mercury. That intermediate heating drives carbon dioxide buildup without stripping away entire atmosphere. Scientists identified 5 particularly promising Venus zone planets to study with James Webb. These targets were selected based on orbital distance, planet size, and brightness of host stars. Brighter stars make atmospheric characterization easier because more light passes through planet atmosphere during transits. Each Venus zone planet offers slightly different laboratory. Different masses affect volcanic activity and atmosphere retention. Different stellar radiation levels change balance between heating and cooling. Different compositions alter cloud formation and greenhouse efficiency. Studying multiple examples reveals which features are universal and which depend on specific conditions. The Venus zone concept helps astrobiologists understand boundaries of habitability. Planets in habitable zone might support liquid water and life. Planets in Venus zone likely cannot. Understanding why requires detailed atmospheric studies. The transition between these zones marks where planetary climate tips from stable to runaway greenhouse. Earth orbits well inside habitable zone for our star. Stellar evolution gradually brightens the source of heat. In perhaps 1 billion years, Earth might enter Venus zone as stellar output increases. Oceans would begin evaporating. Greenhouse effect would strengthen. Eventually, Earth could follow Venus's path to hellish future. This long-term fate motivates study of Venus zone. Understanding the transition helps predict Earth's eventual evolution. It informs searches for life around other stars by defining where to look and where to avoid. It reveals how common Venus-like outcomes might be among billions of rocky planets in galaxy. Some Venus zone planets might have started with more water than Venus, others might have less. Some orbit stars that vary in brightness, others circle stable stars. Each variation provides data for testing models of atmospheric evolution and greenhouse physics. Discovery that super-Venus atmospheres exist validated predictions about Venus zone concept. Theory said such worlds should form under specific conditions. Observations confirmed they do. This alignment between prediction and observation strengthens confidence in underlying physics. Future searches will identify more Venus zone planets. Each one adds to sample size for understanding how rocky planets respond to intense stellar heating. The goal is mapping full parameter space, which combinations of mass, distance, composition, and stellar type produce Venus-like outcomes versus other results. The Venus zone represents both cautionary boundary and scientific opportunity. It warns of thresholds that should not be crossed. It offers laboratories for testing planetary science theories. It connects our neighboring planet to broader cosmic context of how worlds live and die. Meanwhile, Venus itself might be screaming messages we've only begun to hear. Sulfur dioxide spikes in Venus's atmosphere tell stories of eruptions punching through surface. Several spacecraft detected these temporary increases over decades of observation. Each spike rises over days or weeks, then gradually fades as atmospheric chemistry converts gas to sulfuric acid. The pattern matches volcanic activity. Eruptions release enormous quantities of sulfur dioxide from magma degassing. Gas rises into atmosphere, creating temporary spike. Light-driven reactions and acid formation slowly remove excess sulfur dioxide, returning concentrations to background levels. Catching eruption in progress requires luck. Venus rotates slowly, spacecraft orbit relatively quickly. Continuous monitoring from surface perspective is impossible with current mission designs. Observations sample atmosphere intermittently, potentially missing short-duration events. The sulfur dioxide evidence remains circumstantial rather than definitive. Spikes could come from volcanism. They could also result from variations in atmospheric circulation bringing sulfur dioxide-rich air from deeper layers, or from changes in light-driven chemistry altering destruction rates. Proving volcanic origin requires correlating sulfur dioxide increases with other volcanic signatures. Temperature anomalies would indicate recent lava flows. Fresh lava stays hotter than surrounding terrain for years after eruption. Infrared instruments should detect these thermal signatures if they exist. Several studies claimed finding hotspots consistent with active volcanism. Others argued apparent hotspots could be artifacts of how Venus's thick atmosphere distorts infrared emission. Phosphine correlation with sulfur dioxide would strengthen volcanic hypothesis. If same eruptions injecting sulfur dioxide also deliver phosphide from depth, phosphine concentrations should track with sulfur dioxide spikes. Finding that correlation would support volcanic production of both gases. The volcanic fingerprint scientists seek includes multiple independent markers: sulfur dioxide increases, thermal anomalies, phosphine or other reduced gases, seismic activity if detectable, deformation of surface indicating magma movement below. No single observation proves current volcanism. Pattern of correlated signals would. Venus's volcanic features show it was certainly active in past. The resurfacing event covering planet in basaltic lava happened within last 500 million years. That is geologically recent. It suggests Venus's interior remains hot enough to drive mantle convection and melting. Comparing Venus to Earth highlights similarities and differences in volcanic style. Earth has plate tectonics constantly recycling crust. Venus shows no evidence of plate tectonics operating now. Plume volcanism could still occur, with hot material rising from mantle and breaking through crust in stationary locations. Thick atmosphere and high surface temperature on Venus affect how eruptions behave. Lava flowing across surface would not cool as quickly as on Earth because hot atmosphere provides less temperature contrast. Volcanic plumes would interact with dense atmosphere differently, potentially reaching different heights than equivalent eruptions on Earth. Understanding Venus's current volcanic activity matters for multiple reasons. It reveals whether planet interior remains geologically active. It helps explain atmospheric chemistry and cloud formation. It provides context for interpreting surface features mapped by radar. It informs predictions about Venus's future evolution. Future missions need better instruments for detecting volcanism. Long-duration orbiters monitoring same regions repeatedly. Seismometers on surface recording quakes associated with magma movement. High-resolution thermal images mapping temperature variations. Direct atmospheric sampling measuring gas concentrations with precision. Volcanic fingerprints might be subtle. Venus's environment works hard to erase evidence. Heat, pressure, and chemical weathering modify surface features faster than on Earth. Atmospheric circulation mixes gases globally, diluting local signatures from individual eruptions. The signatures should exist if volcanism continues. Proving active volcanism on Venus would transform understanding of planet. It would show Venus remains geologically alive despite hellish surface conditions. It would provide explanations for atmospheric anomalies. It would make Venus more complex and dynamic than static wasteland it superficially appears. The chemistry controlling that atmosphere operates on principles that seem absurd. 96% of Venus's atmosphere is carbon dioxide. The dominance is absolute. No other gas comes close. This concentration creates greenhouse effect, making Venus the solar system's hottest planetary surface, despite Mercury orbiting closer to the star. Carbon dioxide is greenhouse gas. It allows visible light from star to pass through and heat surface. It absorbs infrared radiation that heated surface emits. Absorbed energy cannot escape to space. It stays trapped in atmosphere, maintaining high temperatures. On Earth, carbon dioxide makes up less than 0.1% of atmosphere. Even with this tiny fraction, it significantly affects Earth climate. Venus's concentration is orders of magnitude higher. The greenhouse forcing is overwhelming. Where did all this carbon dioxide originate? Volcanic outgassing represents primary source. Venus's interior, like Earth's, contains carbon. When magma rises and erupts, dissolved carbon dioxide comes out of solution as pressure decreases. This process releases carbon dioxide into atmosphere continuously over geological time. Earth has similar volcanic carbon dioxide output. Earth's atmosphere does not accumulate gas because oceans and geological processes remove it. Carbon dioxide dissolves in seawater. Marine organisms use it building shells. When they die, shells sink, forming carbonate rocks. This carbon cycle keeps Earth's atmospheric carbon dioxide levels relatively low. Venus lost its oceans. Without water dissolving carbon dioxide, and without life-forming carbonates, gas accumulated with no removal mechanism. Every volcanic eruption over billions of years added more carbon dioxide. None was taken away. Concentration built to current overwhelming level. High carbon dioxide concentration affects more than temperature. It determines atmospheric pressure. Carbon dioxide molecules have mass. 96% of atmosphere being carbon dioxide means enormous total mass pressing down on surface. Hence the 93 bar pressure. Density of carbon dioxide exceeds Earth nitrogen-oxygen atmosphere. At Venus surface temperature and pressure, carbon dioxide approaches critical point. It exists in state with properties intermediate between gas and liquid. This supercritical carbon dioxide behaves oddly, dissolving materials ordinary gas would not touch and flowing with unusual fluid dynamics. Carbon dioxide spectroscopic properties make it easy detecting in planetary atmospheres. The molecule strongly absorbs specific infrared wavelengths. This makes carbon dioxide-dominated atmospheres identifiable from vast distances using infrared spectroscopy. Super-Venus discovery relied on detecting these characteristic carbon dioxide absorption features. Greenhouse effect from 96% carbon dioxide follows logarithmic relationship. Doubling carbon dioxide concentration does not double temperature increase. Early carbon dioxide additions cause large temperature jumps. Subsequent additions have smaller effects. Total accumulated effect depends on absolute concentration though. Venus demonstrates what happens when planet's entire carbon budget ends up in atmosphere. Earth carbon mostly sits locked in rocks, buried as fossil fuels, or dissolved in oceans. Venus carbon floats above surface as gas, creating conditions incompatible with any known life. Some researchers propose terraforming Venus by removing carbon dioxide. The idea involves converting atmospheric carbon dioxide to solid carbon and oxygen. Oxygen could potentially react with surface rocks. Carbon would need sequestering or converting to stable compounds. The scale of task is staggering. Moving 93 bar worth of carbon dioxide exceeds any engineering capability humans currently possess. Carbon dioxide domination tells us about Venus history. It confirms runaway greenhouse scenario. It explains temperature and pressure. It demonstrates how losing oceans removes planet ability to regulate atmospheric composition. It shows end result of billions of years volcanic outgassing without any carbon sink. Understanding Venus carbon dioxide helps interpret exoplanet observations. When Webb detects carbon dioxide-dominated atmospheres around other rocky planets, scientists can infer similar evolutionary paths. Chemistry indicates worlds that lost water and fell into greenhouse runaway. Super-Venus category exists because carbon dioxide domination is detectable and significant. The isotopes in that atmosphere remember when things were different. The ratio between deuterium and regular hydrogen in Venus' atmosphere reveals one of planet's darkest secrets. It lost an ocean worth of water to space. The numbers tell story of catastrophic atmospheric escape etched in isotopic signatures. Deuterium is heavy hydrogen with extra neutron. Regular hydrogen has 1 proton. Deuterium has 1 proton plus 1 neutron. Chemically, they behave almost identically. The mass difference matters for atmospheric escape though. When water vapor rises to upper atmosphere, ultraviolet radiation splits molecules. Hydrogen and oxygen separate. Hydrogen atoms, being very light, can achieve escape velocity and fly off into space. Deuterium atoms, being twice as heavy, escape less readily. Over time, this selective escape enriches remaining atmosphere in deuterium. The ratio of deuterium to hydrogen shifts higher. By measuring this ratio, scientists calculate how much hydrogen was lost. Since most hydrogen on rocky planets comes from water, lost hydrogen indicates lost water. Venus deuterium to hydrogen ratio measures about 100 times Earth ratio. Some measurements suggest it might be 150 times higher. This massive enrichment means Venus lost tremendous amounts of hydrogen over its history. Calculations based on ratio suggest Venus might have started with water content similar to Earth, possibly even more. If true, young Venus could have had oceans covering substantial portions of surface. Planet might have been blue like Earth billions of years ago. Loss process took probably billion years or more. As runaway greenhouse-heated planet, water evaporated from surface. Water vapor rose into atmosphere. Stellar ultraviolet radiation broke molecules apart. Hydrogen escaped. Deuterium accumulated in remainder. Eventually, all water boiled away. Hydrogen finished escaping. What remained was deuterium-enriched trace amounts seen today. Process left Venus dry, with only 30 parts per million water vapor in atmosphere. Deuterium ratio provides independent evidence for runaway greenhouse scenario. Other lines of evidence support this history. The isotopic signature offers particularly direct proof though. Numbers come from fundamental physics of atmospheric escape, minimal model assumptions required. Similar isotopic measurements help understand other planets. Mars shows deuterium enrichment, indicating it lost substantial water as well, though less dramatically than Venus. Earth deuterium ratio suggests our planet retained most initial water, protected by greater distance from stellar radiation and stronger magnetic field. Mystery deepens when considering how Venus deuterium ratio varies with altitude. Some measurements show higher ratios in upper atmosphere compared to lower altitudes. This gradient suggests ongoing fractionation processes. Even though bulk water loss happened long ago, isotopic selection continues as water vapor circulates through different atmospheric layers. Ratio also appears in sulfuric acid. Acid molecules incorporate hydrogen from atmospheric water vapor. By measuring deuterium in sulfuric acid, scientists track how water cycles through Venus acid chemistry. Results hint at complex interactions between different reservoirs of hydrogen in atmosphere. Future missions plan measuring deuterium ratios more precisely at multiple altitudes. These measurements will refine calculations of total water loss. They will reveal how water vapor moves through atmosphere today. They will help determine if any water gets recycled from volcanic activity in interior, or if atmosphere is completely cut off from any deep water reservoir. Deuterium signature represents one of planetary science success stories. Simple measurement of isotopic ratios unlocks deep insights about planet history. Technique works because physics determines how light versus heavy isotopes behave. Results are robust and relatively model independent. Venus deuterium ratio stands as testimony to what planet lost. Each measurement confirms Venus was once wetter, probably much wetter. Water is gone now, escaped atom by atom into interplanetary space. leaving behind only heavier hydrogen isotope as evidence of what existed before. What replaced that water paints the sky an eerie yellow. The yellow clouds wrapping Venus are sulfuric acid mixed with sulfur compounds, giving characteristic color. These clouds blanket entire planet in layers up to 65 kilometers thick, hiding surface from visible light observation. Sulfur enters atmosphere through volcanic emissions. Venus' interior contains substantial sulfur. When magma erupts, sulfur dioxide gas releases along with carbon dioxide and other volcanic volatiles. Sulfur dioxide rises into atmosphere, where light-driven chemistry takes over. Stellar radiation drives conversion of sulfur dioxide to sulfuric acid. Process requires multiple steps. Ultraviolet radiation splits carbon dioxide molecules, producing atomic oxygen. This highly reactive oxygen attacks sulfur dioxide, creating sulfur trioxide. Sulfur trioxide combines with water vapor to form sulfuric acid. Acid condenses into droplets at altitudes between 45 and 70 kilometers. These droplets form visible cloud layers, reflecting stellar radiation so effectively. Venus appears bright in Earth's sky because these clouds bounce back more than 75% of incoming starlight. Sulfuric acid alone does not fully explain clouds' optical properties, though. Observations show absorption of ultraviolet light that pure acid cannot account for. Something else must be present in clouds, absorbing ultraviolet and giving Venus' atmosphere yellowish tint. Polysulfur emerges as leading candidate for this unknown ultraviolet absorber. Polysulfur consists of chains of sulfur atoms bonded together. Molecules come in different lengths. Each length absorbs light slightly differently. Mixture of polysulfur species could produce observed absorption pattern. Light-driven chemistry creates polysulfur from sulfur dioxide. Ultraviolet light breaks sulfur dioxide molecules into sulfur monoxide. Sulfur monoxide molecules can then combine and rearrange into various polysulfur species. Reactions involve complex intermediate steps. Researchers continue studying in laboratory settings. Clouds are not uniform. Upper layers contain smaller droplets with higher acid concentration. Lower layers have larger droplets with more water-diluting acid. Below clouds, atmosphere clears somewhat, though thick haze persists. At surface, visibility extends perhaps few kilometers before dense atmosphere scatters light beyond recognition. Winds in upper clouds race around planet at speeds exceeding 350 kilometers per hour. This superrotation phenomenon remains incompletely explained. Atmosphere moves faster than planet rotates, circling Venus in just 4 Earth days. Mechanism driving rapid circulation involves interactions between stellar heating, atmospheric waves, and planet's slow rotation. Cloud particles participate in Venus weather patterns. Droplets form at upper altitudes where sulfuric acid condenses. They grow as they fall through regions with higher water vapor content. Eventually, they reach altitudes warm enough to evaporate. Acid vaporizes, leaving behind any non-volatile components as haze particles. This cycle of condensation and evaporation creates layered structure seen in cloud observations. Clouds are single homogeneous deck. They consist of distinct regions with different particle sizes, compositions, and optical properties. Each layer responds to atmospheric dynamics in specific ways. Sulfuric acid rain forms from cloud droplets, yet never reaches surface. As droplets fall into warmer lower atmosphere, they evaporate completely. This phenomenon, called virga, means Venus has rain that falls without landing. Acid cycles through atmosphere without ever touching ground. Understanding cloud chemistry requires accounting for reactions happening within droplets. Droplets are more than passive containers. Chemistry proceeds inside them, potentially creating new species that then evaporate back into gas phase. This droplet processing might be essential for understanding trace gas abundances and atmospheric composition. Clouds also affect Venus radiation balance. They reflect incoming stellar radiation, preventing some heating. They also trap outgoing infrared radiation, contributing to greenhouse effect. Net result determines how much energy Venus retains versus radiates back to space. Future missions to Venus need instruments sampling cloud particles directly. Collecting droplets at different altitudes would allow detailed compositional analysis. Measuring particle size distributions would improve cloud models. Detecting trace species within droplets versus in gas phase would reveal transport mechanisms and chemical reaction rates. Sulfur clouds are Venus' most visible feature from space. They define how planet appears in telescopes. They control its reflectivity and energy balance. They create environment where hypothetical cloud-dwelling life would have to survive. Understanding these clouds is central to understanding Venus as whole. Beneath those clouds, temperature creates gradient, spanning hundreds of degrees. Venus' atmosphere spans temperature range from roughly -130 degrees Celsius in upper reaches to 470 degrees at surface. This gradient of hundreds of degrees drives circulation, controls chemistry, and defines distinct atmospheric regions. At cloud tops 70 to 80 kilometers up, temperatures drop to frigid levels. Spacecraft entering Venus' atmosphere experience cold before encountering heat. Upper atmosphere radiates energy to space efficiently, cooling to temperatures where carbon dioxide could potentially freeze. Below clouds, temperature increases steadily with decreasing altitude. Greenhouse effect concentrates heat near surface. Thick atmosphere traps radiation so effectively that temperature hardly varies with latitude or time of day. Entire surface maintains near uniform heat. This temperature structure creates stable layering. Cold air sits above warm air. This configuration resists vertical mixing under most conditions. Convection, when it occurs, happens in specific regions or under particular circumstances. Much of Venus' atmosphere remains stratified by temperature. Lapse rate, how quickly temperature changes with altitude, differs from Earth. On Earth, air typically cools about 6 degrees per kilometer of elevation gain. Venus' super-dense atmosphere creates different physics. Lapse rate there approaches adiabatic value, determined by how gases cool when expanding into lower pressure. Temperature affects chemical reaction rates dramatically. Every 10-degree increase roughly doubles reaction speed for many processes. Massive temperature range, from cloud tops to surface, means reactions proceeding rapidly at low altitude barely happen at high altitude. This altitude-dependent chemistry creates compositional gradients. Sulfuric acid exists as vapor in hot lower atmosphere, yet condenses into droplets in cooler cloud region. Boundary between vapor and liquid occurs at specific altitude and temperature. This condensation level shifts slightly with atmospheric pressure variations and local humidity. Water vapor, present in trace amounts, also responds to temperature gradients. Warmer regions hold more water vapor. Cooler regions see water condense onto acid droplets or react with atmospheric gases. Distribution of water vapor through atmosphere reflects this temperature control on saturation. Temperature measurements revealed unexpected structure. Some layers show temperature inversions where air gets warmer with altitude over limited altitude ranges. These inversions might result from light-driven heating, where ultraviolet absorption warms specific atmospheric levels, or from dynamical heating as moving air compresses and heats. Nightside temperature barely differs from dayside, despite Venus' slow rotation. Point on equator spends months in darkness before rotating back into stellar light, yet surface never cools significantly. Atmosphere, heat capacity, and circulation efficiency maintain remarkably uniform temperature. Polar regions show slight cooling compared to equator. Difference measures only tens of degrees though. Venus' thick atmosphere transports heat from equator to poles very effectively. Global temperature distribution remains far more uniform than Earth's seasonal variations. Lightning, if it occurs on Venus, would be influenced by temperature structure. On Earth, lightning requires strong vertical convection, creating charge separation. Venus' stable stratification limits convection, potentially explaining why detecting lightning on Venus has proven difficult. Some researchers argue lightning must occur given sulfuric acid chemistry. Others say temperature structure prevents it. Extreme surface temperature poses greatest challenge for landers. Electronics fail, batteries drain, mechanical parts deform. No material remains immune to heat, approaching 500 degrees. Future Venus landers need heat-resistant designs, functioning just long enough to transmit data. Temperature gradients also affect sound propagation. Venus' dense, hot lower atmosphere carries sound differently than Earth air. Communication systems on landers must account for how acoustic waves travel under those conditions. What works on Earth might fail completely on Venus. Understanding temperature structure helps predict atmospheric dynamics. Heat differences drive winds. Temperature controls where clouds form. Gradients determine stability against convection. Full three-dimensional temperature field defines much of how Venus' atmosphere behaves. Measuring temperature precisely across all altitudes remains a challenge. Spacecraft probe entry gives temperature profiles along descent paths. Orbiting instruments infer temperatures from infrared emission. Ground-based observations sample temperature at cloud tops. Each method has limitations and uncertainties. Comprehensive temperature mapping requires multiple measurement approaches combined. This temperature nightmare formed because Venus walked a path Earth avoided. Venus should have been Earth's sister, same size within few percent, same mass, same density, same rocky composition, both formed at similar times from same cloud of material around same star. Early in solar system history, they likely seemed nearly identical. Then their paths diverged. Orbital distance provided initial difference. Venus orbits about 45 million miles closer to stellar heat. Earth orbits at 93 million miles. That distance reduction means Venus receives roughly twice the stellar radiation Earth does. Early solar system, Venus might have maintained liquid water despite extra heating. The young star was dimmer then. Venus might have inhabited habitable zone billions of years ago. Rain could have fallen. Rivers could have flowed. Oceans might have covered lowland regions. As star brightened over hundreds of millions of years, Venus faced increasing heat. Planet approached threshold where water vapor greenhouse forcing could trigger runaway heating. Once temperatures rose enough, evaporation accelerated. More water vapor meant more greenhouse effect. More greenhouse effect meant higher temperatures and more evaporation. Earth avoided this fate through greater orbital distance and possibly through geochemical luck. Earth carbon dioxide levels remained low enough that water stayed liquid. Plate tectonics recycled carbon into mantle. Life evolved and began affecting atmospheric composition. Earth stabilized in state compatible with liquid water and moderate temperatures. Venus crossed runaway threshold. Oceans boiled away over perhaps billion years. Hydrogen escaped to space. Carbon dioxide accumulated without removal mechanisms. Surface temperature climbed to current extreme value. Pressure built as atmosphere grew denser without gassed volatiles. Some researchers propose Venus might have had plate tectonics early in history. Planet could have recycled crust like Earth does. Without oceans to lubricate process and cool surface, plate tectonics might have shut down. Venus may have transitioned to stagnant lid regime where crust does not recycle. Lack of magnetic field on Venus suggests core is generating different dynamo effect than Earth. This might result from slow rotation affecting core convection patterns, or from differences in core composition. Without magnetic field, Venus' upper atmosphere faces greater exposure to stellar wind stripping, potentially enhancing atmospheric loss. Comparing Venus to Earth reveals how sensitive planetary climate is to initial conditions and feedback loops. Small differences in orbit, rotation rate, volatile content, or geological activity can push planets toward vastly different end states. Habitable zone is region where stability depends on multiple interacting factors. Venus shows what Earth could have become under slightly different circumstances. It demonstrates Earth-like planets do automatically develop Earth-like conditions. Factors making Earth habitable involved combinations of distance, chemistry, geology, and perhaps chance timing of events. Failed twin scenario haunts astrobiology. How many Earth-like planets around other stars might follow Venus' path instead of Earth? How narrow is window between habitability and runaway greenhouse? What early warning signs could indicate planet tipping toward Venus-like conditions? Understanding Venus-Earth divergence helps identify which planetary characteristics matter most for maintaining habitability. Water retention appears crucial. Efficient carbon cycling is essential. Distance from heat source sets fundamental boundaries. Volcanic activity needs to balance between releasing volatiles and enabling atmosphere regulation through rock weathering. Question of whether Venus was ever habitable remains open. If it was, life might have emerged before runaway began. That life would have faced increasing heat and desiccation over geological time. It might have gone extinct as conditions deteriorated. Or possibly, it might have adapted to survive in clouds even as surface became uninhabitable. Venus stands as warning. Planets seeming Earth-like can transform into hellscapes. Process might be irreversible once triggered. Understanding what happened to Earth twin could help ensure Earth does not follow same path. What is certain is that chemistry in Venus' atmosphere operates under rules no textbook predicted. Ultraviolet radiation from the star drives chemistry in Venus' upper atmosphere that would not happen in darkness. Photons carry enough energy to break molecular bonds, creating reactive species that then recombine in new configurations. This light-driven chemistry shapes atmospheric composition we observe. Carbon dioxide molecules absorb ultraviolet photons and split into carbon monoxide and atomic oxygen. Reaction reverses at night when molecules collide without energy input from light. During daylight hours, though, photodissociation creates pools of reactive oxygen atoms attacking other molecules. Sulfur dioxide meets these oxygen atoms and gets converted to sulfur trioxide. Reaction proceeds readily when atomic oxygen is available. Without light-driven chemistry providing oxygen, sulfur dioxide would persist unchanged. The ultraviolet-driven chemistry enables next step, sulfur trioxide combining with water vapor to make sulfuric acid. This acid production happens continuously on Venus' dayside. Process explains why clouds contain so much sulfuric acid. Volcanic sulfur dioxide enters atmosphere. Stellar radiation converts it to acid. Acid condenses into droplets forming clouds. Eventually, droplets evaporate in lower, warmer regions, releasing sulfuric acid vapor back into gas phase. Chlorine chemistry also involves light-driven reactions. Venus' atmosphere contains hydrogen chloride and other chlorine-bearing gases. Ultraviolet light breaks these molecules apart. Resulting chlorine atoms can attack other species, creating hydrochloric acid or chlorine-containing organic molecules. Chlorine chemistry might influence cloud properties and atmospheric chemical balance. Light-driven chemistry creates short-lived radicals existing only briefly before reacting. Hydroxyl radicals, oxygen atoms, sulfur radicals all appear when stellar radiation strikes molecules. These reactive species drive secondary chemistry that would occur with stable molecules alone. Understanding Venus' atmosphere requires tracking these transient reactive intermediates. Day-night cycle affects light-driven chemistry, despite Venus' slow rotation. On night side, reactions requiring stellar radiation stop. Atmospheric circulation brings dayside air to nightside though, carrying products of light-driven chemistry. Nightside chemistry then operates on species created during daylight hours. Full atmospheric processing involves both illuminated and dark side reactions. Altitude determines which wavelengths of ultraviolet light penetrate. Short wavelength ultraviolet gets absorbed high in atmosphere. Only longer wavelengths reach lower altitudes. This wavelength filtering means different chemical reactions dominate at different heights. Upper atmosphere chemistry differs from cloud level chemistry. Models require knowing flux of ultraviolet radiation at each altitude. Amount depends on stellar output, atmospheric composition above that altitude, and angle of incoming light. Researchers build detailed radiative transfer codes calculating ultraviolet penetration. These codes then drive chemical kinetics models predicting reaction rates. Laboratory measurements provide foundation for modeling. Scientists expose Venus-relevant gases to ultraviolet light and measure what forms. They determine how fast reactions proceed at different temperatures and pressures. They identify which products appear and in what ratios. This experimental data calibrates theoretical models. Some pathways remain uncertain. For complex molecules with multiple possible decomposition routes, predicting which dominates requires detailed quantum chemistry calculations or careful experiments. Venus' unusual conditions, high temperature and pressure, make some extrapolations from laboratory work uncertain. Light-driven chemistry potentially affects hypothetical life in clouds. Ultraviolet radiation damages biological molecules. Life in Venus' atmosphere would need protection against chemical destruction. Pigments, protective shells, or living at depths where ultraviolet does penetrate could serve as strategies. Ultraviolet chemistry would represent constant challenge. Production of reactive oxygen species might provide energy for metabolism. Life could potentially harness these radicals as oxidants for chemical reactions extracting energy from reduced compounds. On Earth, some bacteria use light-driven chemistry as energy source through photosynthesis. Venusian life might exploit it differently. Future missions carrying in situ instruments will measure products direct. Sampling atmospheric composition at different local times reveals how concentrations change between day and night. Altitude profiles show where different reactions dominate. Isotopic measurements can sometimes identify which formation pathway produced given molecule. Understanding light-driven chemistry connects stellar radiation to atmospheric composition to cloud properties. Chain of cause and effect runs from star through chemistry to observable planetary characteristics. Venus chemistry represents complex system where multiple feedbacks operate simultaneously, but some chemicals in that atmosphere remember secrets from 4 billion years ago. Xenon, argon, neon, helium. These noble gases do react with other elements. They sit inertly in Venus' atmosphere, bearing witness to billions of years of planetary history. Their abundances and isotopic ratios preserve information that reactive species lost long ago. Noble gases behave as chemical time capsules. They do get locked into rocks through weathering. They do participate in biological cycles. They do form compounds that condense out of atmosphere. They simply accumulate, their ratios determined by planet formation and evolution. Relative abundances of different noble gases reveal where Venus got its atmosphere. If atmosphere came from volcanic degassing, certain ratios should appear. If it came from cometary impacts, different ratios would result. If it resulted from stellar wind capture during formation, yet another pattern would emerge. Venus shows noble gas ratios consistent with volcanic outgassing. Atmosphere likely came from planet interior, released over billions of years as magma erupted and volatiles escaped. This matches high carbon dioxide content, also volcanic product. Noble gases confirm atmosphere volcanic origin. Isotopic ratios of noble gases tell additional stories. Helium has 2 stable isotopes, helium-3 and helium-4. Earth atmosphere has specific ratio between these isotopes. Venus might show different ratio if its interior has different isotopic composition, or if atmospheric escape processes affected lighter isotope preferentially. Argon isotopes reveal age of atmospheric gases. Argon-40 forms from radioactive decay of potassium-40 in rocks. This radiogenic argon then gets released by volcanism. Ratio of radiogenic argon-40 to primordial argon-36 indicates how long volcanic degassing has operated and how much potassium exists in planet interior. Xenon presents particular puzzles. Earth shows xenon depletion compared to cosmic abundances. Venus might have same depletion or might differ. Measuring Venus xenon isotopes would reveal whether depletion mechanism operated similarly on both planets. This connects to questions about atmospheric loss and retention during planetary formation. Neon escapes from planetary atmospheres more easily than heavier noble gases. Its abundance compared to argon indicates how much atmospheric loss occurred early in solar system history when intense stellar wind might have stripped upper atmosphere gases. Venus neon to argon ratio could differ from Earth if atmospheres experienced different loss histories. Past Venus missions measured some noble gases with limited precision. Venera landers provided initial data decades ago. More recent missions added measurements yet did target all isotopes. Key ratios remain uncertain within factors of 2 or more. This imprecision limits constraints noble gases can provide on planetary evolution. Da Vinci mission, launching in late 2020s, will carry instruments specifically designed to measure noble gases precisely. It will determine isotopic ratios for multiple elements. Data will reveal Venus degassing history, atmospheric loss rates, and connections to planet formation conditions. Noble gases might distinguish between competing models for Venus' early evolution. If planet had oceans that later evaporated, certain noble gas signatures should appear. If Venus was always dry, different signatures would result. Inert witnesses sitting in atmosphere today can testify about conditions billions of years past. Xenon isotopes in particular carry information about atmospheric processing. Different xenon isotopes have slightly different masses. Ultraviolet light-driven chemistry can fractionate isotopes, changing their ratios. If Venus' upper atmosphere lost significant gas through chemical processing and escape, xenon isotopes should show distinctive pattern. Comparing Venus noble gases to Earth and Mars reveals how different planetary sizes and distances from heat source affect atmospheric evolution. 3 inner rocky planets started with similar materials, yet ended with very different atmospheres. Noble gases help explain why. Stability of noble gases makes them reliable tracers. Reactive gases like oxygen or carbon dioxide get processed by chemistry, geology, and potentially biology. Their abundances reflect current balance between sources and sinks. Noble gases reflect initial endowment and loss mechanisms. They complement reactive gas measurements by providing independent constraints. Future astrobiological investigations might use noble gases assessing habitability of exoplanets. Measuring noble gas ratios in distant planetary atmospheres could reveal degassing histories and atmospheric retention capabilities. These factors influence whether planets maintain conditions suitable for life. Venus noble gases await definitive measurement. When we finally get those precise numbers, they will answer questions about planet origin, evolution, and relationship to Earth that have persisted for decades. Those same gases float through air that might once have rained on oceans. 4 billion years ago, Venus might have looked very different. The young star burned less brightly then. Venus received less radiation. Planet might have orbited within habitable zone where liquid water could persist on surface. Models suggest early Venus could have maintained oceans for perhaps billion years. During this time, water vapor and carbon dioxide concentrations could have balanced, keeping surface temperatures between freezing and boiling. Clouds would have reflected some starlight, preventing runaway heating. Planet might have been genuinely habitable. If oceans existed, rain would have fallen. Water would have dissolved carbon dioxide from atmosphere. Chemical weathering of rocks would have consumed carbon dioxide and water, forming carbonates. This natural thermostat could have stabilized climate just as it does on Earth. Rotation rate of young Venus remains uncertain. If planet rotated faster than current glacial pace, day-night temperature variations might have driven weather patterns. Cloud formation and precipitation could have occurred in cycles driven by stellar heating. Venus might have had seasons as its orbit and axial tilt evolved. Volcanic activity on young Venus would have resembled Earth, possibly with plate tectonics recycling crust. Oceans would have cooled surface, allowing rigid plates to form and subduct. Carbon dioxide would have dissolved in water, gotten incorporated into carbonate rocks, and descended into mantle at subduction zones. This habitable phase could last. Star brightened over hundreds of millions of years as it aged. Increased radiation pushed Venus toward runaway greenhouse threshold. At some point, feedback loop triggered. Water began evaporating faster than it could condense and rain out. Atmosphere grew wetter and hotter. Transition might have taken millions of years. It might have happened faster. Climate models show that once runaway begins, it accelerates. Process becomes irreversible. Venus crossed from habitable to hellish with no path back. If life emerged during habitable period, it faced increasing stress as conditions deteriorated. Surface organisms would have needed coping with rising temperatures, decreasing liquid water, and changing atmospheric composition. Some might have adapted by moving to high altitudes or latitudes where conditions remained tolerable longer. Most optimistic scenario has life retreating to clouds as surface became uninhabitable. Microbes, originally living in water, might have adapted surviving in acid droplets. This would require extraordinary evolutionary innovation. Billions of years of selection pressure could potentially drive such adaptation, though. Pessimistic scenario is all life went extinct as runaway progressed. Stresses exceeded adaptation capacity. Species died off as environments became lethal. Venus became sterile, water boiled away, and planet reached current state with no remnant biosphere. Determining which scenario occurred requires finding evidence preserved from habitable era. Surface rocks might contain biosignatures if life existed, and if those rocks survived global resurfacing event covering planet in basaltic lava. Atmospheric chemistry might show anomalies traceable to ancient life, even if no living organisms remain. Habitable Venus hypothesis drives much current research interest. If Venus was once habitable, it represents cautionary tale about planetary climate instability. It shows Earth-like worlds can lose habitability. It demonstrates habitable zone boundaries shift over time as stars evolve. Future missions to Venus aim partly testing habitable past hypothesis. They will search for geochemical evidence of ancient water. They will look for minerals forming only in presence of liquid water. They will analyze noble gas ratios that might indicate oceans once existed. Possibility that Venus harbored life makes it perhaps more interesting than Mars to some researchers. Mars might never have had right conditions for life to emerge and thrive. Venus potentially did. If life evolved there during habitable phase, question becomes what happened to it. Understanding habitable Venus informs search for life around other stars. Many rocky planets orbit closer to their stars than Earth does. Some receive radiation levels between Earth and current Venus. These worlds might currently be habitable, or they might be transitioning toward runaway greenhouses, or they might already be post-runaway hellscapes. Distinguishing between these states requires atmospheric characterization. Finding water vapor at levels compatible with liquid oceans suggests current habitability. Finding carbon dioxide-dominated atmospheres with only trace water suggests post-runaway conditions. Super-Venus discovery shows these dead worlds exist around other stars. Venus history connects to Earth future. In perhaps billion years, as stellar output increases, Earth will face similar heat stress. Oceans will begin evaporating more rapidly. Question becomes whether Earth will stabilize or enter runaway greenhouse. Understanding what triggered Venus transition could help predict Earth's eventual fate. What floats in those clouds today makes no geometric sense whatsoever. Clouds of Venus contain particles that are perfectly spherical. This observation puzzled scientists for decades because pure sulfuric acid droplets should be spherical. Surface tension pulls liquid droplets into spheres. Finding non-spherical particles meant something else was happening in those clouds. Multiple spacecraft detected these irregular particles through optical measurements. Way light scatters off particles depends on their shape. Spheres create specific scattering patterns. Observations from Venus showed patterns inconsistent with perfect spheres. Particles had to be aspherical, perhaps elongated or flattened or irregular. One explanation involves solid particles mixed with liquid droplets. If sulfuric acid crystallizes, or if other compounds form solids, those particles would be spherical. Sulfuric acid can exist in different hydration states. Some form solid crystals at cloud temperatures. These crystals could be non-spherical particles. Another explanation proposes mineral dust lofted from surface mixes into clouds. Dust particles are irregular. If surface winds carried dust particles high enough reaching cloud layers, they would appear as non-spherical particles in optical measurements. Required dust transport seems physically difficult though. Ammonia hypothesis provides third explanation. If life produces ammonia that dissolves in sulfuric acid droplets, neutralization reaction creates ammonium sulfate. This salt could precipitate as solid crystals or form semi-solid slurries. Either way, particles would become non-spherical as they transitioned from liquid acid to solid or partially solid salt. Laboratory experiments show adding ammonia to concentrated sulfuric acid does produce solid or semi-solid particles. Reaction is vigorous. Products are definitely spherical. If this process operates in Venus clouds, it would explain observations directly. Non-spherical particles appear more abundant at certain altitudes and latitudes. This distribution might reflect where production process operates most actively. If volcanism or biological activity creates precursor materials, regional variations would be expected. Pattern could potentially distinguish between different formation mechanisms. Particle size measurements reveal another puzzle. Some particles measure much larger than typical cloud droplets. These giants might form through coagulation of smaller particles, or they might result from special formation processes creating large particles directly. Understanding their origin requires knowing their composition. Optical properties of Venus clouds do match pure sulfuric acid models perfectly. Unknown ultraviolet absorber represents one discrepancy. Non-spherical particles represent another. Together, they indicate clouds contain more than just simple acid droplets. Multiple chemical components and multiple particle types coexist. Future missions carrying particle collectors could capture cloud particles and analyze them directly. Electron microscopy would reveal shapes and sizes. Chemical analysis would determine composition. Crystal structure studies would identify minerals or salts. Direct sampling would resolve decades of speculation about what these particles actually are. If particles are ammonium sulfate from biological ammonia production, they represent key biosignature. Finding ammonium sulfate would strongly support life hypothesis, though it would prove life exists without ruling out biological ammonia sources. Particles themselves become evidence in astrobiology debate. Biological explanations for ammonium sulfate remain possible. Lightning could produce ammonia through nitrogen and hydrogen reactions. Volcanic emissions might contain ammonia or precursor molecules. Light-driven chemistry in unusual conditions might generate ammonia without life. Proving biological origin requires eliminating all these alternatives. Shape of particles affects how clouds scatter light and transfer heat. Spherical droplets scatter light according to well-understood theory. Non-spherical particles scatter differently. This affects Venus' energy balance and appearance. Accurately modeling climate requires knowing true particle shapes. Researchers developed sophisticated light scattering codes modeling non-spherical particles. These codes calculate how irregularly shaped objects scatter light at different wavelengths and angles. Comparing model predictions to Venus observations constrains what shapes and compositions are present. Particle mystery demonstrates how observations sometimes reveal phenomena fitting existing models. Rather than forcing data into preconceptions, scientists must consider new possibilities. Non-spherical particles forced reconsideration of cloud chemistry and composition. Those odd particles floating in Venus acid clouds might be mundane crystals or mineral dust, or they might be evidence of active chemistry that models did predict. Or, most dramatically, they might be biosignatures indicating life survives in that extreme environment, determining which requires better data than past missions provided. The tools to get that data are being built right now. Multiple spacecraft will visit Venus in coming decade. After years of neglect, planet is experiencing renaissance of exploration. New missions will deploy better instruments, survive longer in harsh environment, and answer questions lingering for decades. NASA Da Vinci mission launches in 2029. It will drop probe through atmosphere, sampling gases at multiple altitudes during descent. Mission specifically targets noble gas measurements and atmospheric chemistry profiling. It will search for phosphine, measure ammonia if present, and characterize clouds. Da Vinci probe is built surviving Venus environment long enough transmitting comprehensive data. Advanced electronics rated for high temperature. Titanium pressure sphere resisting crushing. Chemical sensors designed for sulfuric acid exposure. Engineering challenges are extreme. Science return justifies effort though. ESA Envision mission will orbit Venus and map surface with radar. Like Magellan mission decades earlier, it will peer through clouds, seeing geology and topography. Envision carries improved instruments, detecting volcanic heat sources, and analyzing surface composition from orbit though. Combination of Da Vinci and Envision provides complementary data. Da Vinci probes atmosphere. Envision studies surface and geology. Together they will address both atmospheric chemistry questions and volcanic activity questions. Missions are coordinated, maximizing science return. Russia and India are also developing Venus missions. Venera D concept proposes orbiter, lander, and potentially aerial platform studying Venus from multiple perspectives simultaneously. India Shukrayan orbiter will carry radar and atmospheric instruments. International cooperation could combine resources and capabilities. Private companies have expressed interest in Venus exploration. Rocket Lab discussed sending probes searching for life in clouds. Mission would be rapid and relatively inexpensive, using small spacecraft on Venus flyby trajectory. Whether this happens depends on funding and technical readiness. Future lander missions face enormous engineering challenges. Heat and pressure destroy electronics quickly. Longest survival time achieved so far is about 2 hours. Extending this to days or weeks requires new technology, high-temperature electronics, advanced cooling systems, or novel designs minimizing electronic components. One proposed approach uses mechanical computing instead of electronics. Gears and levers can operate at temperatures melting circuit boards. Mechanical lander could potentially survive indefinitely on Venus' surface. Concept has been tested in laboratory settings yet never flown. Aerial platforms offer another exploration mode. Balloons or aircraft could float in cloud layers where temperatures are moderate. They could station keep for weeks or months, continuously sampling and analyzing most interesting atmospheric region. Panels would provide power. Acid-resistant materials would prevent degradation. Sample return from Venus has been discussed, yet faces daunting challenges. Returning atmospheric samples requires bringing them to Earth without contamination. Returning surface samples requires landing, collecting material, launching from surface in extreme environment, then transferring to Earth return spacecraft. Complexity exceeds current capabilities, yet might be achievable in coming decades. Scientific questions driving these missions are profound. Is there life in clouds? What is Venus' current volcanic activity? Why did Venus and Earth evolve so differently? What does Venus tell us about exoplanet atmospheres? How do super-Venus planets form and evolve? Answering these questions requires data past missions could provide: more sensitive instruments, longer surface survival times, atmospheric sampling at multiple locations and altitudes, continuous monitoring of volcanic and atmospheric dynamics. New generation of missions aims delivering this data. Venus exploration also serves practical purposes. Understanding greenhouse effects on Venus informs climate modeling for Earth. Studying how planet loses habitability provides warnings about our own world future. Developing technology surviving Venus environment advances engineering capabilities broadly. Renewed focus on Venus represents shift in planetary science priorities. For decades, Mars dominated exploration budgets and attention. Now scientists recognize Venus offers equally important insights. Hellish wasteland next door deserves intense study. Within next 10 to 15 years, our understanding of Venus will transform from sparse data and speculation to comprehensive measurements and detailed models. From debating whether phosphine exists to knowing definitively what chemicals are in atmosphere. From wondering about volcanism to observing eruptions as they happen. Missions to come will either confirm life exists on Venus or rule it out with high confidence. They will either detect active volcanism or prove planet is geologically dead. They will either explain cloud anomalies or reveal new mysteries. Either way, Venus science is entering its most exciting era. And what Venus teaches us could save Earth from identical fate. In 1 billion years, perhaps less, Earth faces same fate that consumed Venus. Star brightens steadily as it ages. Increase is gradual, just 1% every 100 million years. Over geological time, though, this brightening will push Earth toward runaway greenhouse threshold. Process will accelerate slowly at first. Oceans will evaporate slightly faster. More water vapor will enter atmosphere. Enhanced greenhouse effect will raise temperatures by few degrees. This might seem survivable, even beneficial to some regions. Feedback loop is merciless though. More water vapor means more greenhouse heating. More heating means more evaporation. At some point, probably within few 100 million years, balance tips. Runaway begins. Once started, it cannot be reversed through natural processes. Earth oceans will boil over course of millions of years. Water vapor-rich atmosphere will rise to high altitudes where ultraviolet light splits molecules. Hydrogen will escape to space. Oxygen will oxidize surface rocks. Deuterium to hydrogen ratio will climb just as Venus did. Carbon dioxide levels will soar as volcanic outgassing continues without buffering effect of oceans. Gas will accumulate in atmosphere. Temperatures will climb toward Venus-like extremes. Surface will become uninhabitable for all known forms of life. This is speculation. It is physics. Star evolution is predictable. Greenhouse feedback mechanisms are well understood. Boundary between stable climate and runaway greenhouse has been calculated repeatedly by independent research groups. Numbers always point to same conclusion. Earth eventual Venus-like state seems inevitable on billion-year timescales. No known natural process can prevent it. Star will brighten, Earth will heat, oceans will evaporate, planet will transform into wasteland like its twin. Billions of years provide time for technological civilizations to respond though. Humanity, if it survives, might develop capabilities managing planetary climate actively. Stellar shades blocking some starlight, atmospheric chemical removal, perhaps even moving Earth orbit farther out compensating for increased stellar radiation. These sound like science fiction now, Given millions of years of technological development, though, they might become feasible. If humans persist and advance, we might become first species preventing our planet's natural fate through engineering. Understanding Venus provides template for what Earth faces. Every measurement of Venus' atmosphere reveals details about greenhouse processes. Every discovery about how Venus lost water informs predictions about Earth water loss. Venus is Earth future, written in sulfuric acid clouds and crushing pressure. Lesson of Venus is habitability is temporary. Planetary climates evolve. Systems seeming stable can tip into new states. Boundaries between habitable and hellish are absolute. They shift as stars age and planetary conditions change. This knowledge should motivate protecting Earth's current habitability. We exist in narrow window of time when our planet maintains conditions suitable for complex life. That window will close eventually through stellar evolution. It could close much sooner through human-induced climate change, though. Venus demonstrates runaway greenhouse effects are real. They happen to planets. They transform worlds from habitable to sterile. Mechanisms are well understood. Physics is inescapable. Earth is immune simply because we live here. Difference is timescale. Natural stellar brightening gives Earth perhaps billion years. Human activity operates on century timescales. We will trigger Venus-style runaway through carbon dioxide emissions. We can disrupt climate enough, making planet much less habitable for human civilization, though. Studying Venus informs climate science on Earth. Extreme case illuminates principles, greenhouse effects, water vapor feedbacks, carbon cycles, atmospheric escape. All these processes operate on Earth too, just in different regimes. Understanding them in Venus' extreme environment reveals underlying physics. Search for life on Venus connects to Earth, future another way. If life exists in Venus clouds, it represents organisms that survived their planet transformation from habitable to hellish. They adapted to extreme acidity. They learned living suspended in air. They evolved persisting despite conditions killing most Earth life. If such adaptation is possible, perhaps Earth biosphere could partially survive eventual transition at surface, which will become too hot. In atmosphere, though, if microbes evolve right capabilities, Venus' hypothetical cloud life would demonstrate biospheres can persist through planetary catastrophes. Message from Venus is clear. Planets change. Habitability is temporary. Climate can run away into extremes. What happened to Earth twin could eventually happen here. Understanding Venus helps us appreciate how special our current situation is and how fragile habitability can be. Earth will become Venus. Timeline stretches beyond human imagination. Physics guarantees it, though. Our planet will lose water. Atmosphere will thicken with carbon dioxide. Surface will heat to hundreds of degrees. Transformation is written in stellar evolution and greenhouse theory. Until then, we have time. Time studying Venus and learning its lessons. Time understanding processes that claimed our neighboring world. Time appreciating narrow band of conditions allowing life to flourish. And time, perhaps, ensuring that when Earth-Venus-like future arrives, whatever descendants of humanity exist will be ready facing it. Venus shows us our planet's ultimate fate. How we respond to that knowledge defines whether we use warning wisely or squander time we have in ignorance of what is coming. This is why Venus matters. This is why we must understand what happened there. Because one day, Earth orbit will carry us into that same burning zone, and we need to know if there is any escape. The choice is already written in physics. Earth will eventually become Venus unless something unprecedented intervenes. The question is whether that something is extinction, evolution, or engineering on scales we cannot yet imagine. Understanding Venus means understanding the timeline of Earth transformation. Stellar brightening is gradual. We have perhaps billion years before runaway greenhouse becomes inevitable. perhaps only few 100 million years before oceans start evaporating faster than they can be replenished. This seems like forever. In cosmic terms, it is barely a moment. Humanity has existed in recognizable form for only 200,000 years. Civilization has existed for 10,000, industrial technology for 200, spaceflight for 70. The idea that descendants of humans might persist for millions or billions of years seems absurd until you consider that bacteria managed it. Life on Earth has survived 3.5 billion years through multiple mass extinctions. Intelligence might prove just as resilient. If humanity or its descendants survive long enough, they will face Venus' fate directly. No escaping physics, no pretending stellar evolution will somehow stop. The choice becomes adapt or engineer or die. Adaptation might mean leaving Earth, migrating to outer solar system as inner planets heat, building habitats in space, spreading to other star systems before ours becomes uninhabitable. Life retreating outward ahead of advancing heat, buying time until even that becomes impossible. Engineering might mean actively managing Earth orbit and atmosphere on geological timescales, moving planet farther from star using gravitational assists from asteroids, building massive shades in space, blocking percentage of stellar radiation, scrubbing carbon dioxide from atmosphere faster than volcanoes can replace it. Projects requiring energy and resources beyond anything civilization has attempted yet potentially possible given millions of years of development. Extinction might mean failing both paths, technology destroying itself before reaching capability for planetary engineering, evolution failing to produce species able to survive or escape warming Earth, civilization collapsing and never recovering, Earth following Venus into greenhouse runaway, with no intelligence remaining to witness or prevent it. Venus teaches us the stakes. Planet transformation from habitable to hellish is real. Physics makes it inevitable given enough time. No planet orbiting any star will remain habitable forever. Stellar evolution guarantees eventual heating. Question is whether intelligence can recognize threat and respond. The super-Venus planets, James Webb, discovered around other stars, might hold civilizations that faced this choice already. Some might have died with their worlds. Some might have left before end came. Some might have engineered solutions we cannot conceive. We see only dead planets emitting infrared signatures. We cannot know what intelligence existed there or what became of it. Finding life in Venus clouds would change this calculation. If microbes survived planet transformation by adapting to acid cloud existence, it proves life can persist through runaway greenhouse. It suggests Earth biosphere might find similar refuge even if surface becomes uninhabitable. Life could continue even if civilization falls. Proving no life exists in Venus clouds would also teach lessons. It would show limits to adaptation. It would demonstrate some transformations are too extreme for biology to navigate. It would highlight importance of preventing runaway, rather than hoping evolution will save us after it starts. Either answer matters. Either way, Venus holds mirror to Earth future and challenges us to decide our response. The missions launching in 2029 and beyond will provide data enabling better predictions. They will measure atmospheric chemistry precisely. They will detect or rule out biosignatures. They will determine whether volcanism still operates. They will map temperature and composition at all altitudes. They will transform Venus from mystery to understood system. That understanding will feed directly into Earth climate models. Venus represents end point of greenhouse warming. Every detail we learn about how Venus atmosphere works improves predictions about how Earth atmosphere will respond to heating. Every chemical process identified on Venus might occur on Earth under future conditions. Venus is laboratory for studying our own planet fate. The choice between Venus fate and survival starts with knowledge. We must understand what happened there. We must learn why Earth avoided same transformation so far. We must identify warning signs appearing as Earth slowly heats over geological time. We must decide how much climate engineering is possible and whether attempting it creates more risks than it solves. Venus does not offer easy answers. It offers hard truths. Planets die. Atmospheres can become poison. Life zones shift as stars evolve. Intelligence might be universe's answer to planetary death, or intelligence might just be witness to it. What matters is that we look, we study, we learn, we prepare for futures measured in millions of years, even though our lives measure in decades. Venus teaches us to think beyond human timescales and plan beyond human limitations, because Earth will become Venus eventually. Physics guarantees it. What happens between now and then is choice we make through action or inaction. Venus is Earth's future. The only question is whether Earth follows Venus into oblivion or finds another path entirely. That answer begins with understanding what James Webb found 48 light-years away. A dead world, a warning, a challenge, and perhaps, if we search hard enough in those acid clouds, a glimmer of hope that life finds ways to survive even after planets die.